Hello and welcome to another video. Today we're going to be working on combination sum 4. In this problem you're given an array of distinct integers and a target, and you want to return the number of possible combinations that add up to the target. Test cases are generated so the answer can fit in a 32-bit integer. So for this example, 1, 2, 3, target is 4, output is 7 because we can have 1, 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 3, 2, and 1, 2, 2, and 3, 1. So the first combination sum, you didn't want to count combinations multiple times, right? So 1, 1, 2 and 1, 2, 1 were counted as one combination, but now we want it kind of like the order matters, and so we can have different sequences of the same numbers, and they want to count as the same combination. So the way we're going to want to do that is pretty straightforward. We're going to want to do this just like the first one, except now when we pick a number, so let's say we pick this number, and our new target is, let's say we choose to pick number 2 and our new target is 2. Now we can pick any number again, as opposed to before where we said okay, let's just maybe sort these or something, and then if we pick 1, we can either pick 1 again or we can pick something higher, but when we pick 2, we can't pick 1 again because we don't want to go back, right? So if you don't want to go back, you don't want to have something like 1, 1, 2 and 2, 1, 1, but now we do. So actually, at every single iteration, we're going to have to try every single number, right? We don't want to keep track of what we used and what we didn't. We're actually going to try every single number. So what that's going to look like, essentially, is something like this. So let's say our target is 4. We can actually draw this out and draw out all these combinations. So let's give us some more space. And we are going to obviously implement caching, but let's say our target's 4, and we have numbers 1, 2, 3. And I'm just going to say that for anything that gives us a negative number, we're not going to include, because that'll be some base case for us. If the number makes, I guess we can actually handle that in the actual memoization itself. We can just say okay, look, if the number is, if the number that we're subtracting for the target makes our solution negative, let's just not even do that. Okay, so let's figure out essentially how we would do that, right? So let's just go through this. So essentially we have target 4. We can pick any one of these. So let's just say we pick 1. Now our new target is 3, but also we can pick 2. So our new target would be 2, and we can pick 3, and our new target would be 1. Now when we have 3, we want to do the same thing. We can pick 1, our new target is 2, we can pick 2, our new target is 1, and we can pick 3, and our new target is 0. And this is a solution. So now we actually have a solution, right? That's one of them. Okay. So now let's go through this. So we can pick 1, where our new, I might run out of space here, but we'll see. Our new target is 1. We don't even need to really write which number we picked. We just need to more count how many of these paths lead to 0. So we can pick 1, our new target is 1. We can pick 2, our new target is 0. That's also a solution. And we can't pick 3 because then we'd be at a negative target. Okay, now for this one, we can only pick 1. So we would just pick 1, and our new target would be 0. I'm not going to write down what I'm picking. I'm just going to write down our targets. And then we just count these number of zeros, right? Let's actually make this a little bit clearer. So this is a 1, because we picked 1 or the 2. Okay, now for this 2, we can pick 1. Then our new target will be 1. We can pick 2, our new target will be 0, and we can't pick 3. Then for this 1, we will just pick 1, and our new target will be 0. For this one, we will pick 1, and our new target will be 0. And for this one, we'll pick 1, and our new target will be 0. So you can just count out how many different ways you got to the 0. So we have 1, 2, 3, 4, 5, 6, 7, and hopefully that's correct. So that is correct. We have 7 solutions. And we don't really care what numbers we use. We're just counting combinations. So essentially all we're doing is it's pretty straightforward, right? We have some target. We try to subtract every number in the array of nums. Then, if our new target is negative, that's invalid, right? So that's going to be 0. Or we can just check for that beforehand, right? If our new target is negative, we'll just not recurse there. Otherwise, recurse with new target until target equals 0. And then once the target is 0, that is like our base case. So for a DP solution, let's go through it. So for DP, we need three things, right? We need state, 2 base case, and 3 recursive. Okay, so for the state, we're just going to have the target. We don't really care about what index we are on because we're going to try the whole array, right? So we don't really care. Okay, now for the base case, target equals 0. That means we return 1, right? Because that's like a solution. Obviously, if target is less than 0, if we somehow have that, let's return 0. We could do that as well. And then finally, we can use a little bit of tricks to end early. So let's say we have like 1, 2, 3, but our numbers aren't guaranteed to be sorted. And the time complexity of this solution is going to be n squared. So we can actually sort our numbers so we can end early. So let's say we have some numbers, we'll just sort them. So we'll just say they'll always be sorted. Then what we can say is we can have a few more base cases here, right? We actually technically, let me think. Yeah, I don't think we don't need all of our base cases. Yeah, I don't think we need like all of our things, but this is going to help for our recursive case. So if target is less than 0, we're going to return 0. Fine. Okay. Now, what about the recursive case? So the recursive case is literally, and this is where the sorting will help, loop through numbers, subtract target, or actually subtract number from target to get a new target, right? So if our target here is like 4, we would subtract 1 and so on. We get a new target, then we can, just to make it more optimal, then if new target is negative, we can break the loop. Otherwise, keep going. And I'll explain that in a second. So let's say our numbers are 1, 2, 5, 6, and our target is 4. So we would subtract like 1 from the target, and we would get 3, which is fine, right? That's fine for new target. We'd subtract 2 from the target, we'd get 2, totally fine. But now we subtract 5 and we get -1. That means that like 5 can't be in our solution, and because we sorted, anything past 5 also can't be in our solutions. That's why sorting is kind of nice, because essentially in HDP we will have to loop through the whole thing, but as soon as one number is invalid, as soon as one number is bigger than the target, then the whole rest of the array is invalid. So we can save some time there. But that's pretty much it. So we just have a state, we have a base case where the target is 0, we return 1, target is negative, then we have an invalid solution. Then we have this recursive thing where we loop through every single number and we subtract it from the number and we keep going until we either loop through the whole thing or target is negative. And then for each one of those, we will just add, so we will do like our result plus equals DP of using that number, right? So you add up all of these states together. So let's say we had 1, 2, 3, 4. We would say, okay, well, if our target is 4, or let's say we had states 1, 2, 3. So let's get rid of this actually. So we have this, and our target is 4. Then we would say like, okay, our result is something. It's going to be result plus equals DP of 4 minus 1, and then plus equals DP of 4 minus 2, and so on, right? Every possible new state you just add to the result, then finally you cache and you return. So also, yeah, in a base case, you need caching as always, but that's pretty much it. So it's pretty straightforward. All we do is we just loop through all of our numbers, and we just keep trying them all, and for anything that works, we add it to the result. Now we can code. So we are going to sort, like I said, because it does help to make it faster. We're going to have a visited, and then we're going to have a DP that takes in a target. And so if target 0, let's return 1. I don't actually know if target can be negative. Let me think about this. I don't think it can be. Yeah, because we're just going to check for that before, but you can also check, yeah, we're going to check for that before to end our loop prematurely. So I don't think our target can ever be negative because we're just going to check for that before. But we're going to see if we have an error. So we also have to check for visited. So if target in visited, let's return visited target. Whoops. now we are going to do our loop. So we're going to make the result equal 0, and we're just going to say for number in numbers, if the target is less than the number, meaning target minus the number will be negative, let's just break, because that's never going to be a valid solution. So that's why we don't have to check for negative target, because we're just going to be checking here, which will allow us to enter loop prematurely, and it'll save us a lot of time. And then we just do res plus equals dp target number. Finally, we cache it. And we return. And then we need to just return the DP using the original target here. Okay, well, let's see what happens. I don't think we can get negative, so I think this should be fine. Yeah, so you can see it's pretty efficient. Runs all over the place, kind of. I think most solutions are kind of similar, so you can see it's kind of inconsistent as far as the results, but pretty good. So let's think about the time and space here. So obviously for the sorting, that's already n log n, but it's not going to matter because this target can be up to 1,000, right? So if it can be up to 1,000, this is going to be target here. But it's also going to be times the length of nums, right? So if you think about it, for an n log n solution, quote unquote, like sorting this is going to be n log n, which this is like the n part, right? So basically we're saying this is better than, or yeah, sorting is basically free as long as target is greater than log of 200, right? And yeah, and log of 200 is like, I don't know exactly, but you know, somewhere around 10. So as long as the target is greater than 10, this is better, and once the target gets small enough, this is basically linear time anyway. So the sort is going to take longer than the the sort is going to take less time than this part, for unless it's for a very small number, in which case it doesn't really matter because either way it will be fast. So if you wanted to, you could get rid of the sort, and you could get rid of the sort, and you could get rid of the break, and then you could say if target is less than 0, return 0. This should also technically work, I believe. It will just theoretically be slower. Yeah. So it is a little bit better the other way, or you know, a decent amount better usually. So, whoops, and there we go. Okay, so that's going to be roughly this. You can, if you want to, you can say like, well, you know, maybe the sort might take longer, so you could say like plus n log n if you wanted to, which would make some sense. But yeah, so assuming your target is bigger than the log n, which it almost always is, it's going to be faster that way. Okay, and for the space, so what do we have here? So we have this visited, and visited can have any number up to target, so the space is just going to be O of target. Oh yeah. And I think that's actually going to be it for this problem, so not too bad. And then they asked, what if negative numbers are allowed? How does this change the problem? What limitations do we need to add? So actually, I believe with the sorting, I think it's just fine, I want to say. Like, we can test some stuff, but I want to say it would just work for anything because we're kind of doing the same thing. As long as we sort, I think it would be totally fine, and it would work right there then. You could test it on your own if you wanted to. I'm not going to do it in this video, but yeah, that's going to be it for this one. If you like this video, please like it and subscribe to the channel. It helps grow it a lot. So I'll see you in the next one. Thanks for watching.